With this lecture, we will start to talk about vectors versus applied vectors, and it will be the last chapter of the course of linear algebra. Now, arguably, this lecture and the next one are the most important in all the course, because they really deal with the notion of vectors and applied vectors, and this subject has been contaminated by physicists and engineers, and to make it mathematically sound, it requires a considerable amount of work, and especially one should try to forget about what he has been told previously about these notions and start from scratch completely. One of the most misleading concepts in mathematics is the one of applied vector. Let's analyze this expression. So applied vector is comprising two words. The first is an adjective, applied, and then a noun, vector. Therefore, semantically, applied vectors are a subset of vectors, because applied vectors are a special kind of vectors, are those that are applied. We see now that the semantic expression does not have a mathematical counterpart, and indeed, for the use that everybody makes of these objects, applied vectors are not vectors. But let's start from the beginning. Key question: which vectors are they subset of? By definition, vectors are elements of a set on which there is additive structure, which means that I can take two elements of this set and sum them up and still get another element of this set. And I can also take these elements and multiply them by scalars. The set of scalars or the field of scalars is a completely different set, whose elements can be multiplied with the elements of our initial set. So if this set has these two structures, an additive structure and a multiplicative structure with the elements of a field, then this set is called a vector space, and its elements are called vectors. Now, if we say that applied vectors are indeed vectors, as semantically implied, then we have to find what is the vector space of which these vectors are the elements of. Definition: an applied vector is a pair A, B in V squared, where V is a vector space. So an applied vector mathematically can be described as a pair of usual vector in a vector space. Most people draw applied vectors as arrows. In R², for example, we write them like A, B, an arrow on the top, and we draw them with an arrow starting from A and ending in B. So A is the starting point and B is the ending point of this arrow. And we call A the application point, hence the name applied vector. Let's go back to the initial question. Of which vector space applied vectors are elements of? So how can we sum these vectors up? How can we sum applied vectors among them and still get an applied vector? So big problems appear when they want to sum applied vectors together. They refers to those who wanted to draw vectors or applied vectors as arrows. Which applied vector is A, B plus C, D? The most obvious thing to do is to use the sum structure of the Cartesian product of V times V. Applied vectors are elements of this vector space, and this vector space inherits the vector space structure from its factors, so from V in this case. For instance, the sum in R4 for applied vectors of R², because if v is r squared, the Cartesian product of v times v is going to be isomorphic to r4, or the sum r6 for applied vectors of r3. However, they insist that it should be the fourth vector of a parallelogram obtained by translating CD by A minus C. So those who advocate this approach in handling applied vectors or vectors in general, they put constraints on the geometrical interpretation of the sum and multiplication by scalars. So let's try to chase these constraints in a mathematically precise way and see where we are heading to. They insist that if we take AB and we draw it as an arrow, and then we take CD and we draw it as an arrow, the sum of AB plus CD must satisfy the following geometrical construction. We translate CD in such a way that C ends up coinciding with A. So we have to sum both C and D by the vector A minus C. Okay, if I sum C with A minus C, I end up getting A. And if I sum D with A minus C, I end up getting this vector right here, geometrically, which algebraically is written as D plus A minus C. And then the sum of the applied vector AB plus the applied vector CD is defined to be the fourth vertex of a parallelogram generated by the three vertices A, B, and D plus A minus C. So this one right here. This is what people claim that should be the definition of the sum A comma B plus C comma D. Okay, this vector right here. Well, there is a big problem in using this definition for the sum of two applied vectors. Nice try. Unfortunately, commutativity of the sum does not hold with this definition. That is, AB plus CD is not equal to CD plus AB, which makes this sum not possible as a sum in a vector space. Okay, so this definition of sum cannot be used in a set on which applied vectors are elements of in order to make it a vector space. And why is that the case? Because remember, to sum AB plus CD, we had to translate CD to make C coincide with A. Now, if we sum CD plus AB, we have to translate AB in such a way A will coincide with C. Therefore, the parallelogram will have as an initial vertex, if you wish, C, and the sum will be the fourth vertex of the parallelogram, starting with C, and then having D as a vertex, and then having as a vertex another vertex right here, which is the image of B by the translation. Okay, now if we sum, and if we construct the parallelogram with these three vertices, C, D, and the translated of B, that will be right here, we will end up with the vector in here. Okay, and this vector is different from this other vector, whether we want to see it as an arrow pointed in any kind of direction. Okay, so commutativity does not hold using this definition. Some of the more enthusiasts notice that although these two sums of applied vectors are different, there is a translation sending one to the other if we assume that the sum has as application point, in this case A, and in this case C. Okay, so another convention to be used. So what? So let's try now to mathematically chase even this kind of objection or justification that these people bring up, and see what it would take mathematically to make it to make all these hands waving and holes patching sound. Okay, so define M to be the set of applied vectors, or if you wish to think about them as arrows, of a vector space V. Since they are not able to define a proper sum from the Cartesian product of M times M to M, which would give the set of applied vectors a sum structure, they define a map from M times M to M modulo an equivalence relation, where the equivalence relation between two applied vectors is given by the existence of a translation E expressing C as a translated of A and D as a translated of B. So AB is equivalent to CD if and only if there is a translation sending C to A and D to B. Okay, so they say the sum we are getting here, if we commute the summands, is not commutative, but it becomes commutative once I project down this definition that I've given of a fake sum down to M modulo this equivalence relation. Yes, but this structure then is no longer on M. So it is not a structure that gives a closure of M with respect of this structure, because the codomain of this sumoid structure, let's call it sumoid, this sumoid structure is no longer in M, but it is in the quotient of M. And this causes some problems. We can try to solve these problems mathematically, saying that sumoid factors through M modulo the equivalence relation times M modulo the equivalence relation. So in this case, we do have a structure of sumoid over not the set of applied vectors, but the set of applied vectors modulo this equivalence relation. So mathematically, this means that this sumoid operation factors through the projection of on each of the factors of the Cartesian product going on the same equivalence relation down. So we have the Cartesian product here of M modulo equivalence relation in both factors. And then we have a map going from this Cartesian product of M modulo the equivalence relation times itself to M equivalence relation. And we can call this sumoid plus structure. Now, so indeed there exists a map going from here to here, but this map does not operate on applied vectors, but operates on equivalence classes of applied vectors. So it is not a structure on M, it is a sum structure on M modulo the equivalence relation. At this point, one should check that the same can be done, though, with the multiplication by scalars, because this is not the unique structure we need to make a set a vector space. We need the sum, but then we need also multiplication by scalars, and possibly also other structure that we analyze in the course, like scalar and vector products. So for each of them, we have to check that they all factor through this new set of applied vectors modulo the equivalence relation. So this is what it would take to make mathematically correct this kind of hands-waving and intuition that physicists usually want to impose to the notion of vectors and applied vectors. Does this seem didactically sound for a first-year undergraduate student? So that is the question I'm really posing. Probably this is not the right way of approaching the concept of vectors and applied vectors, and we have to rethink the whole argument from scratch. And we will see this in the next lecture.